And today we will talk about a rule called the chain rule, a very important rule that will allow us to differentiate compositions of functions. What is the sign of the square root of x? Say if I'd like to evaluate sine of the square root of x when x is equal to, say, 2, what would you do? On your calculator, if you have an old calculator, you would probably hit 2, the square root of x, and then sine. So let me write down this process. So you start with 2, then you apply the square root function, and then you get the square root of x, and then you apply sine to get sine of the square root of x. So we have 2 steps here. We apply 2 functions, and the inner one is the square root of x, the outer one is taking the sine. So if I denote the composition by capital F of x, then the inner function g of x will be the square root of x, and the outer function, lowercase f of x, will be equal to sine of x. And then we could write down that f of x, capital F of x, is the composition of f and g. Sometimes the composition is denoted as f circle g. Okay, let me try a couple other examples to see if you can decompose this composite function into 2 functions. How about e to the negative t squared? That function is quite important in statistics. It's related to the bell-shaped curve. Okay, so what do you do first? If you need to evaluate, it's f of t. If you need to evaluate this function at t, you first raise t to the second power and take the negative of that. And then you exponentiate the result. So t will go to negative t squared, and then the result will be exponentiated. So the inner function g of t is negative t squared, and the outer function is e to the t. Notice that this function actually is a composition of 3 functions, because you can think of g of t as the composition again, as the composition of the outer function taking the negative of a number, and the inner function just a squaring. But the point is that if you have a composition of many functions, always you can separate the outermost one and then treat the rest as one for the moment. Okay, let's try one more. How about f of alpha to be cosine sine alpha? Well, many students will think about that expression as the product of cosine and sine. But obviously this does not make sense. There is no multiplication sign here. Cosine is a function, so it needs an argument. What could be the argument? Sine? Sine is a function, so it needs the argument. The argument is alpha. So this function is actually equal to cosine of sine of alpha. So the outer function here is f of alpha to be cosine alpha, and then the inner one is g of alpha to be sine of alpha. Let's now try to find the derivative of the following function, 3x plus 1 raised to the second power. Three x plus 1 raised to the second power. So how would you find the derivative of this? Well, you might be tempted to apply the power rule. X to the second power, the derivative of that gives you 2x. So if I were to apply this rule to this function, I would get 2 times 3x plus 1. And a lot of students will do that, and they'll get 0 credit, because you cannot apply the power rule to functions, to powers of functions other than just x. What we need to do here, if we're not equipped with any general rule that will tell us how to differentiate a function like this, we would probably need to expand this expression first and then differentiate. So let me do that. What's the quantity in the parentheses? 9x squared plus what? 2 times 3x times 1 plus 6x plus 1. So 9x squared plus 6x plus 1. And then we differentiate this quadratic expression. And actually, this can be differentiated because you could do it term by term. So the derivative of the first term, what's the derivative of 9x squared? It's 18x, right? It's 9 times 2x. So 18x plus the derivative of 6x is 6, and the derivative of 1 is 0. Okay. So we got the derivative, and notice that if I factor out 6 here, I get 6 times 3x plus 1. So formula looks a little bit like the power rule, but it's not quite the power rule, right? If I split 6 and write it as 2 times 3, this is what I'm going to get. But notice that this 3 is the derivative of the inner function here, right? Because what is it? Here x goes to 3x plus 1. That's my function g, and then the result is squared. So the outer action is f. So 3 is the derivative of the inner function, and the derivative of the outer function, lowercase f of x. So g of x is 3x plus 1, and lowercase f of x is equal to 2x. Sorry, it's equal to x squared. So the derivative of x squared is 2x. So basically that's the derivative of f, but not evaluated at x, but at 3x plus 1, so at g of x. And that will be the power, the chain rule. So I like to state the chain rule in general, and we will do several examples. Okay, so let me now state the chain rule in general when we have a composition of two functions, f and g of x. So x goes to g of x, and then we mapped g of x to f of g of x, and I will denote that action by the composition of f of g of x. And here we are assuming that the function f and g are differentiable. G is differentiable at x, That means the derivative exists at x. And then f is differentiable at g of x. So the chain rule states what we just discovered by looking at this particular example, 3x plus 1 squared, that the derivative of the composition f prime of x is equal to the derivative of the outer function evaluated at the inner function g of x times the derivative of g of x. So we will apply this rule to various examples. Before I do that, let me write down the chain rule using Leibniz's notation. We probably will not use Leibniz's notation as much in this class, but because many of you are science majors, you will use Leibniz's notation quite often there. So let me do that. Well, let u to be equal to g of x, and the variable y be equal to f of u. So then the derivative of capital F of x is dy by dx. So notice y is a variable, but it depends on u, but because u depends on x, so y is a function. It depends according to a function of x, which is the composition of f and g. So this expression is dy by du, and the derivative of g of x is du by dx. So notice that actually using Leibniz's notation, it's easy to memorize this rule because it seems like du's cancel, but don't think about it too much this way because these symbols cannot be separated. They're derivatives. I will do one example using both notations, and then you can pick which one you like more. I don't want to make you feel biased, but I actually prefer the Pram notation. Okay, so let's go back to our original example. Remember, capital F of x was equal to sine of the square root of x. So here, the inner function g of x is the square root of x. And then the outer function, f of x, is equal to sine of x. So we'll need the derivatives for the chain rule. So g prime of x is the derivative of the square root function, which is 1/2 x to the power negative half. Remember why? Because the square root function can be written as x to the power 1/2. So we apply the power rule, and the power rule states what? You decrease the exponent by 1, and you multiply this by the exponent. So it'd be 1/2 x to the power 1/2 minus 1. That's why I have negative half here. Okay, and the derivative of f, from the last lecture, remember that the derivative of sine of x is cosine of x. Okay, so we're ready. So, what do you get? F prime of x is equal to f prime of g of x times g prime of x. So, f prime is cosine, but you do not evaluate cosine of x, but you evaluate cosine at the argument. And g prime of x is 1/2 x to the power negative half. So that's the answer. Once you get real proficient with the chain rule, you don't need to even write down what f and g are, but for the purpose of this homework, I do recommend that you do that. And actually, some problems may explicitly state to write down what the outer function is and the inner function is as well. Let me illustrate the same example using Leibniz's notation. So here, u is equal to the square root of x, and y is equal to sine of u. So du by dx, we'll need that, is 1/2 x to the power negative half, and then dy by du is the derivative of sine, so that's cosine u. So dy by dx is equal to the product of dy by du times du by dx. So this is cosine of u times 1/2 x to the power negative half. And you don't want to have u at the end, right? Because you want to have a function of x. So you have to write down what u is. So it's cosine the square root of x times 1/2 x to the power negative half. Well, pick your choice. Again, I would not use this method because there are so many letters, so many variables. I would just use the chain rule using the prime notation whenever possible. Okay, so now we will move on to some other examples. And I would like you to differentiate e to the power x to the third. So let f of x be equal to e to the x to the third. And I want you to find the derivative using the chain rule. So what's the inner function for e to the x squared? X first goes to x cubed, and then we exponentiate the whole thing. So the derivative of x to the third power is equal to the derivative of the outer function, which is e to the x, but we do not evaluate the outer function at x, but at the argument, and the argument is x to the third, and the derivative of the inner function, which is 3x squared. So that's the answer. Okay, how about another example? Let f of x be equal to cosine of sine of x. So the derivative of cosine sine of x will be equal to, the outer function is again cosine, the inner function is sine. Remember that there is no product here. So the derivative of the outer function is, what's the derivative of cosine? Remember, last lecture, trigonometric functions, it is negative sine. Don't forget that negative. So it's negative sine. And here you evaluate that negative sign not at x, but at the argument. So it'd be at sine of x. And then you multiply that by the derivative of the inner function. The derivative of sine of x is cosine of x. So that's the answer. So this was the derivative of the outer function evaluated at the inner function. And cosine of x is the derivative of the inner function. G was sine and F was cosine. The chain rule can be applied several times, and perhaps that's the reason for the name of the chain rule. So let me illustrate an example where we will apply the chain rule twice. And if you see a function that's a composition of three functions, then what you do is you first think about it as the composition of the outermost function and the rest. Then you apply the chain rule. And then you will have to do it again because the inner function is, again, the composition of two functions. Let me see. Let me look at one example. And there will be many other examples in the homework. How about this one? Sine of tangent of t squared plus 1. Now we need to differentiate this composite function. So first, the outermost function is what? Sine, right? So I will treat sine as the outer function, and everything inside I'll treat it as g. So the chain rule, if I apply it the first time, I get the derivative of the outer function. So that's cosine evaluated at tangent of t squared plus 1. Again, remember that this is cosine of, so maybe I should use parentheses, of tangent of t squared plus 1. There's no product here. Times the derivative of tangent of t squared plus 1. So that was the chain rule the first time. And now we will apply the chain rule one more time. So I have to rewrite this term. And again, there's no need for parentheses here, but I'm just writing so it's clear that cosine is applied to all of it. Times, now what's the outer function in the bracket? It's tangent, right? So we apply the derivative of tangent, which was, the last lecture, it was secant squared. Secant squared evaluated at the inner function times the derivative of t squared plus 1. So finally we get cosine tangent of t squared plus 1 times secant squared of t squared plus 1 times 2t. Once you get really proficient with the chain rule, it will be okay to write everything in one line, but again, for the purpose for this homework, so that our staff will know that you understand the chain rule, I'm asking you to do it step by step. And in the initial homework problems, where you need to identify the outer and inner function, please write down what they are, like f of x is equal to, and g of x is equal to. Okay? Let's now consider one more example. Okay, so we'll conclude this lecture with the derivation of the formula for the derivative of an arbitrary exponential function. Well, remember the derivative of e to the x is e to the x, and the reason how we got that, or remember sort of the rationale, was that if you look at graphs of exponential functions, and if you look at their tangents at 0, 1, e to the x at slope, the graph of e to the x at 0, 1, that slope was exactly 1. Well, it's not the case for, say, 2 to the x. Let me sketch 2 to the x. So that would be 2 to the x, and more or less that was e to the x. The slope at 0, 1 of 2 to the x is a little bit less than 1. So certainly it is not true that the derivative of 2 to the x is 2 to the x, because if it was the case, then at 0, the derivative of 2 to the x at 0 would be 2 to the 0, which is 1, so that slope would be also 1. So probably there is something missing here in this formula. And we will now derive a general formula. We will derive that the derivative of a to the x is a to the x times a number, and that number is ln of a. We'll apply the chain rule in this derivation. The trick is to rewrite a to the x as a composition, as the composition of two functions. And in order to do that, just remember that if you raise e to the power ln of anything, say of b, you get that number b again. And that is because exponentiation and taking the logarithm are inverse functions. So if you apply one and then the other, the result is the original argument. Okay, so I will write a to the x as e to the power ln of a to the x. So I'm essentially just letting b to be equal to a to the x. And the reason for this is that then I can rewrite the exponent here as e to the power x times ln of a. Remember, logarithms have these nice properties that if you take the logarithm of something to a power, you can factor that power outside of the logarithm and write it as a product. So basically, I wrote a to the x as the composition of two functions here. The outer one is exponentiation, and the inner one is a linear function. So let me see what's happening here. Again, x goes to x times ln of a, so that's just multiplying x by a number. And in case of 2 to the x, that number will be ln of 2, which is more or less 0.067, something like this. Okay, and then, so the outer function will be exponentiation. So then we get e to the x times ln of a. Okay, so we're ready to differentiate a to the x, but we will write it this way. Okay, so the derivative of a to the x is equal to the derivative of e to the x times ln of a. Now applying the chain rule. So the derivative of the outer function is the exponential. I evaluate the outer function at the argument. So this would be my f prime of g of x from the chain rule, remember? And then I multiply it by the derivative of the inner function. And the inner function here is just a linear function. You multiply x by this number ln of a. So its derivative will be just ln of a. So this was g, and this was f. Let's look at that expression and see if we can simplify it. Well, e to the x times ln of a, we actually wrote this down, what it was. E to the x times ln of a is just a to the x. So our final answer is a to the x times ln of a. And that's exactly what I promised you that I would prove. So, for example, the derivative of 2 to the x is now 2 to the x times ln of 2, which is approximately 0.67 times 2 to the x. Let me illustrate one example where I will apply this formula. That formula is important, and please remember it. You will need it on the exams and in the homework. Okay, so let's differentiate 8 to the power pi x squared. So we have to think about this as a composition. So the outer function is a to some power, and the inner function is pi times x squared. So first let me calculate what the derivative of a to the x is. According to this formula, it will be a to the x times ln of 8. So if I apply the chain rule to our example, I get, what do I get? It's a good time to pause me and finish that example before I continue on the board. Okay, you already have it? What is it? The outer function is a to the x. So what's the derivative? It's a to the x times ln of 8 times the derivative of the inner function. Well, it's not exactly that. We need to take the derivative of the outer function, but we don't evaluate that at x, but at the argument. So it'd be 8 to the power pi x squared times ln of 8. So that's the derivative of the outer function. And then the inner function is pi x squared. So after evaluation of the second power, of the second derivative, I get this.